Right, so let's look at question 6 of the tutorial. So we're given the standard molar entropy of ammonia gas at 298 Kelvin and its heat capacity, and so we're given the heat capacity as a function of temperature. In other words, it implies that its heat capacity is not constant or independent of temperature. It is a function of temperature, and then they say the coefficients are as given in Atkins's resource section. So let's quickly just get to the resource section. So that's there in this table. So for ammonia, it's there. So it's A, B, and C. Let me just get up there. So we just need to also take note of B is to the power 10 to the power minus 3, and C is to the power 10 to the power 5. So let's write them down. So in other words, CP, oh, I'm on green. I don't like green for writing formal stuff. Okay, so CPM of ammonia is equal to, well, A, it's 29.75. Then, oh my goodness, plus 25.10 times 10 to the minus 3t plus, well, it's actually minus because C is minus 1.55 times 10 to the power 5 over t squared. So that's what C's formal form is. Okay, and then we're asked to calculate the standard entropy at 100 degrees Celsius. So that is then 398 Kelvin. Right, 398 Kelvin. Okay. Oh wait, goodness, that's not 398 Kelvin. It's 373 Kelvin. Whoops, I almost made a very big boo-boo there. Okay, right. So, what are we dealing with? We're dealing with a heating process. So we have to look at entropy changes in terms of heating. So what is the definition of entropy for heating? The definition of entropy for heating is delta S is equal to, well, Ti to Tf of Cp over T dt. That's the definition of entropy when heating is involved. And then normally what we would have done, so just as like a little side note, let me just put it in a block here. If Cp was independent of temperature, so Cp independent of T, in other words, it's not a function like we have here. Then we would have said, well, delta S is equal to Cp integral of dt over T, which is just equal to Cp ln of Tf over Ti, which is the equation which you are very familiar with and you've used 745 times, right? And of course, if this is a molar function, then there's an n that comes in front of here. Anyway, right, so this becomes molar. Okay, so that is extremely important for you to be aware of. This is actually, so we just need to update this slightly. So this is, if it's molar, so then everything becomes molar. So that is if the Cp is independent of temperature. But if it's dependent of temperature, we cannot take it out of the integral and do that we did there on the right hand side. And we have to leave it inside the integral, and we actually have to integrate it as such. So whatever the function is we're given, so there's the function as given. So what we have here is we have the integral from Ti to Tf of A over T plus B over, or bt over t plus c over t squared let me write it like that, divided by t, right, dt. So you see I've just taken every term there in the CPM function and divided it by t. So divided it by t, divided it by t, divided it by t. Okay, and that is then equal to the integral of a over t plus b plus c over t cubed dt. Okay, so delta S molar, oh, we can call it standard actually now if we want to. We can make this standard because it is standard, is then equal to, so let me split up the integrals, ti tf of a over t dt plus the integral of ti tf b dt plus the integral of ti tf c over t cubed dt. Right, which is then equal to, okay, so a, b, and c are just constants, right, which we wrote out there at the top. You know, we have values for them, so we don't have to worry about them. So I'm going to just rewrite this without having to rewrite the equation all the way. So this just becomes 1s everywhere. There's a b outside, there's a c outside, there's a 1 there. Okay, so what is the integral of 1 over t? Okay, it's ln of that. I don't know who I was waiting for to answer, but anyway, it's ln of t. Okay, you don't really know about absolute values, but anyway, so let's just so between ti and tf, right, plus b, and the integral of just dt is just delta t, right, but it's just t. So let me put these things in like block brackets. I'm always unsure what kind of notation to use, because it's people from biochemistry and people from hectic mathematics and physics people and clowns and whatever in my class. So anyway, and then the final one, this one is a bit more complex, but anyway, so the integral of t cubed is going to be a half 1 over t squared, but minus a half t squared between ti and tf. Okay, so let's think about it. So each of these, so ln of t is going to give us 1 over t, that's fine. The differential of t is just 1, so that's perfectly fine. The differential of minus a half 1 over t squared is going to be minus 2 goes down, so that becomes 2, that's fine. Subtract 1 more, t cubed, that's fine. Okay, now we just have to plug in the tf's and ti's. So a, we have ln of tf minus ln of ti plus b of tf minus ti plus c times minus a half. Okay, I'm going to take the minus a half out. Minus a half c times 1 over tf squared minus 1 over ti squared. Okay, Here we use our logarithmic rules, so the ln of A minus the ln of B becomes the ln of A over B. So like that, but then of course you don't write A and B, you idiot. You write Ti and Tf. Goodness sake, I need to sleep. Then B delta T, because that's what delta T's definition is. And this one I can't really simplify much more, so it just becomes minus C over 2 1 over Tf squared minus 1 over Ti squared. Okay. Right. That of course is equal to, as we said, our molar change in our molar entropy. So that's the change. We wanted to calculate the entropy at 373 Kelvin. So how do we then get the entropy, well, at 373 Kelvin? Well, the change in entropy would just be equal to the entropy at 373 Kelvin minus the entropy at 298 Kelvin. So in other words, we just need to take this term to the other side. Right, so this term just needs to go across the equation. So let's make it do that. So I'm going to rub this out. So therefore, delta S, no, not delta S, delta, therefore SM373 is equal to SM at 298 plus what we call delta SM, you know, so plus all this stuff that we wrote here. Okay. And then we have the absolute pleasure to now substitute all this in. So SM at 373 is equal to, okay, so we're at least given the entropy at 28298 Kelvin, which is 192.45 joule per Kelvin per mole, because we're working with molar quantities. And then we have all these other things. Okay, so then we need to substitute. So then we had A plus, or A times the ln value. So we had 29.75 joule per Kelvin per mole times the ln of the two temperatures. So 373.15 over 298.15 plus 25.10 times 10 to the minus 3 joule per Kelvin to the minus 2 per mole to the minus 1 times 75 Kelvin, because that's the change in temperature, minus a half C, which is minus 1.55 times 10 to the 5 joule. Okay. Then in the end, you see the first one is in joule per Kelvin per mole, so there's nothing that cancels out. The only thing that cancels, there's a Kelvin that cancels with that. This is all in joule per Kelvin per mole. So it's actually a Kelvin. It's actually not per Kelvin. This is just Kelvin. Yeah, joule Kelvin mole, because it cancels with the Kelvin squared per Kelvin squared that's over here. So all the units are fine, and it's 200.7 joule per Kelvin per mole. Minus 1. Cool. Which is the answer after all that work. Okay. I don't like these types of questions where you have to calculate a lot of things. I would typically ask you and then you could stop here. I would just say, like, write an expression for calculating. I mean, it's a lot of unnecessary work, this. Like, why? Computers can do that for you. Okay. Yeah, so of course, if the CP were independent of temperature, what would we have done? Would have done that. Now, because it isn't independent, it's that. And remember, I can give you any type of function that's dependent on the temperature and give you coefficients, and you will need to be able to calculate how the entropy changes. I could give you that CPM is equal to e to the power minus t over alpha, and then tell you calculate the entropy change. You understand? Because it's just a function. It's a function of temperature. So, and then tell you whatever alpha is. Alpha is 7, for example. And if we just figure out the units, I might do something like that because I'm weird. Yeah, so that's essentially the bottom line from this question. I think the most challenging part, of course, is the integration. It's always the integration, because nobody vibes with maths, because the pass rate is like 30%. So anyway, yeah, I think that is it for this question. If you didn't follow, just watch the video again.